friend and colleague, Professor Rick Kazman, traveled dearly and also lost his bag twice, thanks to Skipple, or Schipple, as someone has referred to it in the past few days. I guess we can use that microphone so you don't have to stick with this.
Oh, yeah.
Here. Yes. When you get to be a professor, this is the treatment you get. From associate professors.
Rick, you need to share the picture.
Pardon me?
You need to share
Yeah. It's important. We'll get to that in a second.
I'll just do this. You're going to stay seated, right?
No.
Oh, sure. Sorry.
Okay, it's here.
Slide that.
Slide. Actually, if I can put this over here. That's what I was afraid of. Yes. All right. So thank you, Damien. Thank you all for attending and for inviting me here. It's my pleasure to give this talk. My name is Rick Kazman. As you can see, I'm from the University of Hawaii. There's a little nod to Greece, our host country. It's a picture of the myth of Sisyphus. And you may know Sisyphus was a god who was punished by Zeus for defying death, and was sentenced by Zeus for his punishment to roll a boulder up a mountain, only at the end of the day to have it fall down and have to repeat this for eternity. And this is a metaphor for our task as software architects. I don't know what I'm doing. Okay, I won't move. This is a metaphor for our task as software architects. So this has been my research challenge for all of my career, is how to make the task of architecting, designing complex systems, analyzing them, visualizing them, to make it more tractable, to make it something that average software engineers can do. This is the current state of the practice in software development, and I see some of you are laughing and nodding your heads. If you've ever been involved in the development of a non-trivial software system, you feel for this guy, because he's working really hard and he's probably making very little progress. And the question is, why? The boat is leaking, but you keep paddling, and why would you do this?
Because you get paid.
Because actually, that's a very good reason, because you have to report to your manager. And there is a little bit of progress. You are getting the boat forward a little bit. You're working as hard as you possibly can. And the reason you can't convince your manager to do otherwise is, I would claim, the lack of measurements. There's no way, there are a few good ways to quantify the amount of debt in the system, the degree to which you're being held back by the boat being full of water, right? The rational thing to do is to pull the boat onto shore, bail out the water, patch the leaks, then get back in the water.
Want to use this one?
Yeah.
It's a bit less dangerous.
For our readers.
Okay, I'm attached. Oh,
Don't destroy your only shirt.
is this okay?
Yeah.
All right, yeah, since leaving home, my luggage has been lost twice. So since arriving in Europe, I've actually had my luggage in my possession for about 4 hours. The rest of the time, it's been somewhere in airport land. Okay, so, and And I claim that part of the problem is that design is largely invisible. It is not visible to managers. It is not visible to most developers. What they see is code and code-type artifacts. And there was a study performed by the Software Engineering Institute about 5 years ago where they interviewed over 100 architects and project managers. And one of the results of that interview was that they found that design debt was the costliest and most pernicious form of technical debt because it's hard to spot. You can't find it easily because it is diffuse, it is distributed among the many artifacts in a software development project. So one of my big research goals over the last decade or so has been to try and identify design flaws, the things that hold you back, the kind of accumulated technical debt, which, right, every one of these design decisions was made for a reason. Right? Every single one was a deliberate choice by someone. Just like every line of code that you write is a deliberate choice. No one ever writes code thinking, how can I make this code worse? How can I make it harder to understand, harder to maintain? How can I make it so that 6 months from now, even I won't understand, right? No one ever has that conversation, but design accumulates. So this is the tangled nest of dependencies, sometimes called the big ball of mud. Sometimes we get interface mismatch or differing assumptions between two parts of a system or two systems that need to collaborate. And sometimes we just get the strange design decision, one that you just say, what were they thinking? Oh, by the way, I took this picture. This was
Is it in Korea or something?
in Buenos Aires, in the Opera House. In
It's a
Buenos
real
Aires.
picture.
Yeah. Okay, so as I said, design debt is the worst kind of technical debt. So how can we measure this? How can we measure the health of an architecture? Every architecture has flaws. Yes, your system that you're working on has flaws. I guarantee it. I've analyzed hundreds at this point, and I've never seen one that did not have design flaws. So really the question is, can this be automated, given that every system has it, given that they could accumulate any time by the action of any designer, right? One misplaced API call could introduce a design flaw to your system. And how can this be empirically justified? What's our empirical basis for this? And since we aspire to be an engineering discipline based on science, this should be repeatable. Okay, so isn't this a solved problem? We already have technical debt detection tools, right? Structure 101, SonarQube, Sonar Source, Designite. No, unfortunately. So we did a study last year, but there have been a couple other studies comparing technical debt detection tools, and they have all come up with the same conclusion, which is that the tools are unreliable. They are unreliable in terms of producing the same results on the same data set, and they are unreliable in terms of the results that they produce actually being connected to things that you care about, like bugs and effort, churn. So in our study, we looked at 6 different tools, and they disagreed about even the most basic measure of software, like how many lines of code are in this module. They disagreed on that. And even worse, what they reported was no more insightful than big files are bad. And you knew that already without having to spend $20,000 a year on a license. But it gets worse. Existing tools only analyze static relationships, right? And the title of this talk was about the architecture of Web 4.0 systems, and Web 4.0 systems, like all systems, are likely to be distributed systems. with a certain amount of autonomy. They're going to be dynamic. They're going to be increasingly built from dynamic languages like Python and Ruby as a set of microservices. And so I'm going to call these for short in this talk DD systems, dynamic and distributed systems, just so I don't have to say that each time. So these are the architectures of Web 4.0 systems, by and large of the systems of our future. And if we're already having a hard time analyzing today's systems, yesterday's systems, which were largely monolithic systems, you build an executable, you deploy that executable, and we already had a hard time analyzing those and understanding their architectures and managing their technical debt. What do we do about these more complex systems, these more dynamic systems, and can this be made automated and repeatable? So let me first talk about the state of the art using DV8, which is a tool that I helped to create, and then we'll get to the more researchy part of this talk. So I said this needs to be empirically justified and repeatable. The empirical basis for what I'm telling you is over 300 open source projects, more than 50 open source projects. In fact, we're probably over 100, industrial projects, probably over 100 industrial projects by now. So what we do is we have a process of automatic data collection. We extract information from source code repositories, from revision history, from issue tracking systems. We turn the big flaw analysis crank, which spits out a set of design flaws, and then we talk to the architects. We collect feedback and we say, are these in fact causing problems? Are these the sorts of things you would like to fix, to refactor? So just to put a little bit more meat on the skeleton here, in our data collection we extract a project's source code and we do a light reverse engineering on that. So we're only interested in extracting the relationships between modules. So class A inherits from class B, or method in class A calls method in class B, or type A extends type B. So it's kind of lightweight extraction, but we're trying to understand the dependencies between the parts of the system. So we end up with a file dependency report. We then look at the revision history of the project, what changed, for what reasons, and what commits. And we look at the bug reports or the issue tracking system so that we understand when a file was changed, when a commit was made in the revision history of the project, what was the reason for that commit? Was it to fix a bug? Was it to implement a new feature? Was it to do a refactoring? And so forth. So these get, this information, this extracted information is represented as DSM, a design structure matrix, just a square matrix that allows us to annotate relationships between entities. And we have a SDSM structural DSM to represent the structural relationships. A calls B, A inherits from B. And we have a history DSM to represent the history relationships. File A changes together with file B. Right? They were co-committed. They were committed in the same commit to resolve the same issue. And these give you different and mutually reinforcing views to understand how project complexity is evolving. And then we do a number of analyses, so we calculate some architectural metrics, which I won't be talking about in this talk, but there's papers on them at decoupling level, propagation cost. But we also detect architecture flaws, here called architecture issues. And we generate some reports, we quantify the cost of these flaws, because when you go to talk to a project manager, what they're interested in is cost and schedule. How much is this costing me? How much is it going to cost to fix? What would be the benefits if I fix it? We need to quantify this. Otherwise, it's very difficult to get management to do anything. And then, as I said, we talk to the project personnel, the developers, the architects, the project managers to collect feedback. So as I said, we collect dependency information, history information, and information about issues to know the reason why a commit was changed. And we cluster the files or the modules of a system into something called a design rule space. Now, this is based on the research of Baldwin and Clark, in this book, Design Rules, where they talk about how design rules are a organizational concept for any complex system, right? So they weren't, in this book, they were not talking just about software, although software is the foundation for the most complex artificial systems ever created. So any subset of files can form a design space, and design spaces are led by a design rule. So you can think of a design rule as an important interface in a system. If you have an abstract factory pattern that you apply in a system, there's an abstract factory class, and then you can have concrete factory instances you can have specializations of that abstract factory that inherit from that class, and then you can create concrete instances in a system. So there will be a whole bunch of files that depend on that design rule, on that abstract factory definition. And this is true of software design in general, right? Think of APIs and the importance of APIs. There are going to be a lot of files that implement an API and a lot of files that use that API. The API is the design rule, and these files that depend on that design rule are its design rule space. So any non-trivial software system will contain many design rules and design rule spaces. Every feature that's implemented, every pattern, every concern can be viewed as a design rule. And so any given file might participate in multiple DR spaces, because a particular file may participate in an abstract factory pattern and a visitor pattern, and may be part of some logging and some exception management and so forth. So it might participate in multiple DR spaces. And as I said, we visualize these as design structure matrices. So I'm sure you've all seen these. These have been around in engineering design since the 1940s or 1950s. The idea is you list all of the things in your system along the rows of the matrix, square matrix, and you list those same things in the same order along the columns, and you put a mark in the cell where thing on the row depends on thing in the column, right? So these might be components. You might model communication between people or between teams. You might model information flows. So DSMs have been used for all kinds of different analyses. We're using these to analyze the relationships between software and as you'll see, teams. So then we do the automated analyses. So we do measurement. As I said, I'm not going to talk about this, but there's metrics that we produce. But what I am going to talk about is the design flaws that we can find in systems and how we quantify that to determine design debt. So I'm just going to skip over the metrics because I don't have much time. Let me talk about flaw detection. So as I said, every architecture has flaws, lots and lots of flaws, and these weigh down the evolution of an architecture. So we've identified over the years 6 classes of flaws: unstable interface, modularity violation, crossing improper inheritance, tweaks, and package cycles. And why should you care? You should care because they matter. They're highly correlated with bugs, changes, and churn. So the more that a file participates in a flaw or several flaws, the more likely that file is to be buggy or to be change prone. It's going to require a lot of effort on the part of development teams. This is why managers care. So here's an example of an unstable interface. So you see the file on the second row, utils.fb utilities. There are many, many other files that depend on this file. So in the column 2, we annotate the dependencies on file in row 2. And you see almost every file depends on, that's what the DP annotation here means. And the number after the comma indicates how many times the file in each particular row co-changed, was co-committed with utils.fb utilities. So you can see lots and lots of co-commits and lots of dependencies. So FB utilities is an important leading file, an important design rule, but it changes frequently and lots of other files have to change when it changes. That's bad, right? You want APIs to be stable. Here's another kind of design flaw, crossing. This is simply a file that has high fan in and high fan out. So we see here at this file in row 5, lots of other files depend on it and code change with it, and it in turn depends on and code changes with almost every other file in this DSM. All right, it's a tangled web of dependencies, like that picture of the electrical wires that I showed at the beginning. Modularity violation is a little more subtle kind of design flaw. So what you see here is a set of 27 files, and the DSM is mostly empty. There's a few annotations. This file creates that file, this file uses that file, but it's mostly empty. And empty generally means good. It means these files don't have much dependency on each other. That suggests you should be able to change one without changing the others, which is what we hope for, what we like in a modular system. However, when we look at history information, we see a very different picture. When we look at the code change numbers, we see large numbers of code changes, especially in this central subsystem. So what does this mean? It means these files have hidden dependencies, semantic dependencies not reflected in an API. So I'll give you an example. When I did an analysis of OpenSSL a few years ago, and OpenSSL is a horribly structured system, one of the worst I've ever analyzed. Yeah, and it's the underpinning for what, 90% of e-commerce websites today? Scary. There was one change in particular which had caused a security bug that was well reported. And this security bug, what it was you could send a request to have something encrypted with a 1 million bit encryption key. So they didn't put a limit on the size of the encryption key. So someone would send a request to have something encrypted with a huge encryption key. OpenSSL would just say, okay, 1 million bit key, start encrypting. And the web server would come to its knees, right? It couldn't handle the processing load. Okay, so this bug was reported. OpenSSL developers sprang into action. And it took them, I think it was 20 commits before they found all the files that actually cared about the length of an encryption key. So this information was scattered among many modules within OpenSSL. This was an example of a modularity violation. That information that should have been modularized, should have been encapsulated in some API, but was not. And so when you make that change, you have to change file A and file B and file C, D, E, F, G, and so forth. So here's an example from an open source project. It's kind of an old one, but it applies. And as I say, you can find these flaws in any modern systems. This is from JBoss. Here we see the class JDBC store manager, which aggregates a whole bunch of command classes above it, as well as the cache class, read ahead cache. So it is aggregating these other classes. But then we look at the command classes and we see that they in turn aggregate JDBC store manager. So there's a cycle of dependencies among those classes. And what we see is that relation data manager up at the top in row 1 is in a modularity violation with these command classes. So you see these code change numbers are very high between relation data manager and the command classes, but there's no structural dependency between any of those files. So yes, this is from another open source project, Cassandra. And here we see an unstable interface. So FB Utilities is an unstable interface. Lots and lots of files code change. And here we see a cyclic dependency. These two files code change with each other. And here's another cyclic dependency. So what is it? SS table reader inherits from SS table, and SS table depends on SS table reader. All right, this is a no-no. Okay, so lots of flaws. Do you care? Do they matter? So interesting research question is, if a file is involved in a flaw, is it likely to be more buggy, more change prone? And if it's involved in 2 flaws, 3 flaws, 4 flaws, right? Since a file can have many relationships with many other files, it could be involved in multiple flaws. So in our initial study, we looked at 10 projects, 9 open source and 1 commercial. And we counted the architecture flaws in these projects, and we compared them on a file-by-file basis with bug frequency, bug churn, the number of lines of code that it required to fix the bug, change frequency, and change churn. And here are the results. Any questions? Okay, don't be a jerk. So here is a table that summarizes the unreadable results from the previous slide. So this, we look at the set of all files among all 10 projects that had 0 flaws. So some files are good, they don't participate in a design flaw. And on average, they had 0.1 bugs, resulting in 3.7 lines of code, and 0.5 changes, resulting in 29 lines of code. As we go down and look at the set of files with 1 design flaw, 2, 3, 4, we see that the number of bugs goes up, the amount of bug churn goes up, the number of changes they're involved with goes up, and the change churn goes up. And this shows the Pearson correlation coefficient, looking at the correlation between the number of design flaws and these various measures, and it's always about 0.9, which is a very strong correlation. We've in fact done some causal modeling work, and it does indeed look like these are causal. What about security bugs? So that was for bugs in general. What if we just look at security bugs? Because those are the kind you should really be worried about. And so we did the same study with a similar set of projects, but now in addition to the original measures, we looked at the frequency of security bugs and the amount of churn associated with fixing those. This was our set of projects, 11 open source projects. And again, on average, we see pretty consistently about a 0.9 correlation between security bugs and and architecture flaws, as well as similar correlations with the other measures. So the point of this is these design flaws really matter, and they really matter for things that you should really care about in your software system. This is rust at work. This is entropy at work that is slowing down your development velocity, slowing down your release velocity. We can do even a little bit better than that, which is we can look at the costs of these flaws, and we can calculate a return on investment if you were to refactor them. So we've done a number of case studies with industry where we did just that. We convinced them to do some refactoring. That cost them something. They had to spend some person months of effort to refactor. And then we calculated what would the likely return on investment be. So this was with a company called SoftServe, and here we calculated the 3 worst DR spaces in the project, and we looked at the files and the flaws in those files, and we calculated how many defects those files were experiencing per year, how many changes they were experiencing per year, the number of lines of code committed to fix those defects and make those changes, And then we reported each of the design flaws to the architects, and we asked them to come up with a plan for refactoring. And that was fairly easy, because if you have, let's say, an unstable interface, well, you need to refactor the interface. If you have a crossing, you need to break that file into some smaller sub-files that have fewer inbound and outbound dependencies. If you have unhealthy inheritance, you have a parent class depending on a child class, you probably need to move some methods from the child class up to the parent class. So, by identifying the flaw, you can easily identify a refactoring strategy. So the architects, armed with this information, said it was going to cost them 14 person months to refactor, to remove the most grievous flaws, and then we can come up with an expected benefit, an expected savings. And the calculation there was, by removing the flaws, these files should regress back to the norm, regress back to the average. So instead of being really terrible, buggy, and change-prone, they will go back to being average files in the project, right? So you may say, well, that's kind of a big assumption, but remember, we have this causal relationship between flaws on the one hand and bugs and changes and churn on the other hand. Or if it's not causal, it's very close to causal, right? So it is reasonable to assume if you remove the root cause, these files should regress back to the norm. And I'll show you some examples of where that actually worked. So based on this, we have an expectation of 41.35 person months of savings in the first year alone for an expense of 14 person months, 300% ROI. This is something you can take to a project manager and say, you should do some refactoring. Because if you don't have these numbers, right, remember the guy who was rowing, and I said one of the problems was the lack of measurements. If you don't have the numbers, the conversation goes like this. Project manager, we would like to do some refactoring. Project manager says, great, how many new features will that get me? Architect says, 0, it's refactoring. Project manager says, hell no, get back to work. Right? Without the quantification, you can never make the justification, the business case for refactoring. So we've done a bunch of industrial case studies. We worked with ABB on analyzing 8 of their systems. These were large industrial control systems, power plants, water treatment facilities, things like this. These are long-lived industrial automation software embedded systems that were expected to live 30 or 40 years. And we analyzed these systems. We reported the results back to them. And they all said that the reports gave them quantifiable results, which made it easier to go back to management and argue for refactoring or a rewrite. 6 of the 8 projects, as a result of this, began a refactoring project, and one of them, they just decided to do a complete rewrite of the system because it was, well, they said that in this particular project, they had to budget a person month of effort for a 1 line of code change. They were not proud of this, but that was just their reality. We also did work with Huawei to do this kind of instrumentation into their corporate quality control process. And again, a significant number of those found positive correlations between these measures and productivity. I'll spend a couple minutes talking about this company, BrightSquid. This is a Canadian company. They build a secure communication platform for healthcare professionals, doctors, dentists, clinics, and things like this. And what we did is we captured a year's worth of their project history as the before state. We convinced them via this one of these kinds of report to refactor. And so they had a 3-month refactoring period. And then we calculated their after state. We captured 6 months of project history. And, whoops. And their refactoring did indeed reduce the number of bad things in the project. So you see the number of cliques went from 17 to 10, the number of unhealthy inheritance went from 60 to 30, the number of unstable interfaces went down, the number of crossings went down, and so forth. So the refactoring actually worked according to our automated analysis, but more important was the results. The refactoring took them 563.8 person hours. They shrunk their code base. They got rid of a lot of code clones. And they found that the average time needed to close issues before and after refactoring went down by 72%, and the average bug fixing churn went down by 2/3. So it was taking them on average 102 lines of code to fix a bug before the refactoring, now 34 lines of code after the refactoring. And oh yeah, and their bug fixing duration dropped by 30%. Okay, so these results are primarily for old style systems, monolithic systems. What about DB systems? These pose some new challenges for us. So think about writing systems in dynamic languages. This is the same simple example written in Java code and written in Python code. So a non-dynamic language versus a dynamic language. And what we see is that there's a visitor pattern here. And if you look in car element visitor.java, it has to have a dependency on each of the classes that it visits. Right? That's just the way the visitor pattern works. If you look at the same code in Python, it looks like those dependencies are mostly gone. But they're not, they can't be, right? For the visitor pattern to work, it's just that you don't see the dependencies because of the dynamic nature or the weak typing in Python. Fortunately, we can resolve most of these possible dependencies using type inference, or sometimes called duck typing. So if you're not familiar with that, it's based on looking for similarities in the signatures, the API signatures, right? If it walks like a duck and quacks like a duck, it's probably a duck. And so based on that, we can recover most of those possible dependencies and disambiguate them. So we looked at 105 Python projects. On average, 75% of the were explicit, but about a quarter of them were possible dependencies, ones where static analysis could not definitively determine what the dependency was between files. But of those, well, 24.28%, we could recover 14.28% of those using type inference, which means that 90% of the static dependencies can be unambiguously determined. So that's good news. It means we can get close to the kind of analysis we do with non-dynamic languages. And these matter. These implicit dependencies matter. So a file involved in possible dependencies or implicit dependencies, ones that you cannot check with a type checker, require 30% more maintenance effort than a file involved in explicit dependencies. Why should that be? Well, because we're humans, right? If the compiler can't see this dependency, that means you as a human have to do some extra work to figure out how that dependency is actually resolved. So this is a high impact for these possible dependencies, and so it's really important that we do as much automated resolution of these dependencies as possible. How am I doing for time? Am I out of time? 5 minutes. Okay, perfect. I'm almost done. Okay, so DD systems, dynamic and distributed systems. We looked at dynamic very briefly. What about distributed systems? These pose additional challenges. So right now, DB8 takes in as input source code dependencies, change information, but in distributed microservice systems, each microservice is probably its own repo, maintained by its own team, talking to its own database. And so these are a lot harder to analyze. There's no single place that you can go to find ground truth. So for dynamic systems, of course, we want to still extract compile time dependencies, including the explicit and possible dependencies that I just talked about, but also API dependencies. But even more subtle than these, data dependencies and semantic dependencies. So if two components process similar data entities or share the same database, we consider that they have a data dependency. If two components have textual similarities, we consider that they have a semantic dependency. Now, these are not going to be precise, right? We might get some of them wrong, but as long as our F-score is reasonably high, this is a valuable kind of analysis to do. We can also look at build dependencies. We can get these from Maven or NPM or other kind of build tools. We can get runtime dependencies. We can extract these from execution logs. And we can also look at ownership relations. So which team maintains which repositories? If two services are maintained by separate teams, there's a chance that they don't talk to each other, they don't communicate with each other, or that their communication might be more complex or more expensive. So here, for example, is a DSM showing team-based interactions. So we see here that team 4, in this row here, depends on the infrastructure services created by team 1, and the 8 here is actually exponential. This means that there are 2 to the 8th API calls to infrastructure services. So all of these numbers here are exponential. In addition, the infrastructure services depend on many, many services created by the distributed teams. So that looks like an anti-pattern. What about data coupling? Here we see in the 4th row, TS cancel service and TS config service are highly data coupled. And in, what is it, the 11th row, TS admin order service and TS admin basic info service are highly coupled. There it is. They share 72 data entities. So this is still early in the research project. We feel like we have a really good handle on capturing architecture flaws in old-style systems, monolithic systems written in non-dynamic languages, and we're just embarking on expanding this analysis to these DD systems. So we're looking at team coupling, data coupling, evolutionary coupling. If change to some entity always causes other entities to change, either through bug fixing or feature addition, then we consider them to be evolutionarily coupled. We can look for crossings among the APIs. The same thing, are there lots of APIs that this API uses and lots of APIs that it depends on? That looks like a crossing. We can also look for retiring components from execution logs, see which components are seldom or never called, or repetitive components, where, like code clone, where we see the same functionality appearing over and over again in different components. So this is our research agenda. So, done. Lessons learned. There's enormous debt, design debt, in today's software. Yes, in your software. That's bad news. The good news is we can do something about it. We've shown this in study after study, and it's possible to automatically and objectively assess architecture quality. We can find and we can fix the debt. And although it's still research, we have hope that we can extend this to DD systems. So we think it's possible to bridge the gap with, by this I mean the gap with management. Our results have been enthusiastically received by many industrial projects. Most of them we convinced to actually do the refactorings. Some companies have even incorporated this into their into their development pipelines. So final thoughts. You can't manage it if you don't measure. Quantification is key. If the measurement isn't automated, it won't be done, or it won't be done often, or it won't be repeatable. So these need to be built into the build process and reported in a management dashboard of some form. And this leads to improved architectures, and we have very strong evidence for this. And dollars or euros matter, right? If you can't relate this to the bottom line, you won't get uptake. Oh, and the software, at least for academic use, is free. You can take a look and download it. So I'm done. Happy to take any questions. And I'm happy to share my slides. I have a long list of references at the end.
Could be. So I guess we have time for a couple questions. I think there's an extra microphone somewhere.
Thanks for that fascinating talk. I think it's totally fascinating that you can quantify these things. I mean, it makes architecture into a real scientific subject. I was wondering, how do you manage to do the automation of the analysis, in particular regarding stuff like static code analysis, which is very hard to write. I mean, and it's very hard to write it so that it's robust vis-a-vis multiple programming languages, vis-a-vis multiple versions of programming languages and systems. How do you manage to do? I mean, I can understand you can automate, for example, the analysis of what comes out of a version control system. That's probably a completely different pair of shoes, right?
Yeah.
But static analysis at the code level, how do you manage to do that?
Yep. Great question. So there's two answers to that. One answer is we outsource. So we use an open source tool called Depends, which does dependency extraction from a number of languages. And for languages that Depends doesn't understand, we use the commercial tool Understand. And so, good name for a tool. And remember, it's a simpler job than true reverse engineering of code, because all we need to extract is the dependencies between code modules, right? Type dependencies, inheritance, calling relationships, aggregation relations. We don't need to actually understand the code. So it is a simpler problem.
You probably also don't need to be 100% precise, right?
Right.
I mean, the statistics can absorb some.
Yeah. So the comment is we don't need to be 100% accurate, and that's absolutely right. If what we're dealing with here is finding the worst trouble spots, and so if something is 10 or 100 times worse than the best file in your system, if you're off by 2% or even 10%, it's still the worst file in your system. Yeah. So the precise details kind of don't matter. And that's because it's architecture, right? If I was looking for a security flaw, yeah, every line of code matters.
Yeah.
Thank you for a very interesting talk. It was also very accessible for a newbie like me. What I found very interesting is you mentioned a lot of flaws in architecture. They were intuitive flaws. I could understand why they would work, and you showed that they correlated highly with bugs and with churn. Did you come up with these flaws beforehand based on literature and then validate them with your measurements?
Yeah, so it was an iterative process of analyzing code, talking to architects. Some of these came from the literature, so things like cycle of dependencies, we didn't invent that. Things like a high fan in, high fan out, we didn't invent that. So some of these came from our own prior research, like the modularity violation was our own prior research. Some of these came from literature, and as I say, we tried as much as possible to validate these with our interactions with industrial protection.
So you also did the other way around, where you looked at files that had a lot of bugs, a lot of churn, and then found the patterns that would come with those, the flaws.
Well, you can't just look at the bad files, because remember what I said at the beginning, is big files are bad. So every file that has a lot of lines of code is going to tend to have more bugs and more changes and more churn, but that by itself doesn't mean it participates in design flaws. It probably does, but that's not a ergo kind of proposition.
Thank you.
I think one more question, that's it. Anyone? All right. Yes.
About the static dependencies and the language where they're more or less explicit, and now all this Python style, non-type stuff or whatever. How hard is it to get by with respect to these problems if in maybe the foreseeable future, maybe 90% is non-typed or poorly typed and so on? What's the cost for that?
Yeah, so in cases like that, as I said, we can recover a significant number of the possible dependencies by using type inference. But in the cases where we can't, we can still resort to instrumentation of a system and tracing. If A calls B, that's unambiguous, right? And so we've done some experiments where we compared our static extraction with dynamic extraction. And it's not perfect, of course, but we can get reasonably high, 0.9 or better precision in recall. Thank you.
All right, let's thank our speaker again. I guess we have a short coffee break now then, and then let's resume in, how are we doing on time?
15 minutes. So
Yeah,
normally
okay, so
always set
15 minutes, coffee break, and then let's resume. Quarter to 2.
Great.
Yes. How are you guys along with that? I mean, is this, because this is not published, right?
The stuff about dynamic
aside from what I did tonight. Let me back to my phone. Yeah, I'm going to stick around for the next
as it is, because it's very nice. Og vi laver nogle lidt professionelle standarder til hvor de urvarer til de laver de urvarer det samme som det her opgave hvis man viser så forudschaffen og dann heißt es immer nach dem jeweiligen Stand der Technik. Ja, man hat doch gar keine Interesse daran. Das ist ein Grund, warum auch dieses bei der externen Interessiert wofür mich engagiert ist. Das heißt Compliance. Okay. Dann hast du diese Interaktion zwischen NOAA und Technologie. Die EU, die wollen wirklich sagen, das haben sie mit GDPR gesagt. GDPR ist ja viel leichter. Der X wollen sie ja viel mehr. Das heißt, das ist jetzt gegen sagen, so, das darf man nicht machen. das müsste das lassen. Dann kommt die Frage, wie können wir das prüfen? Wie können wir das prüfen? Das ist eine Hilfe an Schluss. Ja, und dann kommt jemand und sagt, ja, das wird nicht gesagt. Das ist auch das Problem. Das kommt von der Es ist auch